I think the session 3 will get started. Is learning in networks. So I am your second chair, Zhang from Microsoft Research Asia. So the first talk actually is let's welcome the first talk presenter, Zirui. Zirui is a fourth-year PP student at Peking University, where he is advised by Professor Huang. His research focused on LLM system and machine learning for computer networks. He is currently on the job market and exploring research opportunities in both academia and the industry. So let's welcome him to present KaeTE.
Hello. Thanks. Good afternoon. I'm Zirui. Today, I'm going to present our work, KaeTE, towards practical neural traffic engineering with Lagrangian Duality and learning to optimize. This is joint work with Yanghao, Jie, and Chen. Traffic engineering, TE, needs to solve a new optimization problem on a regular basis, for example, like 5 minutes. Typically, a centralized TE controller repeatedly closes loop. It observes the current topology, link capacities, and traffic matrix. It then computes root ratios among a pre-computed candidate path set. One of the most important and practical TE objective is maximizing throughput, which is the total volume of the emitted traffic. And linear programming LP solver can find the exact optimum, but its latency can become the bottleneck when traffic on network conditions changes faster than the soft cycle. In contrast, learning-based TE solvers can have low computation overhead, which makes them attractive. Before we go on, let's formalize the throughput objective for each source. For each source destination commodity ST, DST is the traffic demand. PST denotes its candidate path set between S and T, and RP is the emitted fraction based on candidate path set P. The objective sums emitted traffic over every commodity and path. There are two kinds of constraint. Specifically, the first constraint keeps each commodity within its demand budget and enforces non-negative ratios. And the second defines link utilization. The total traffic routed through link E divided by capacity CE is defined as the link utilization. It must be at most 1. In reality, the network topology, the link capacities, and the traffic demands may evolve over time due to failure or maintenance, which results in dynamic network conditions. However, there are still some limitations on existing learning-based TE solvers, which makes them less practical. For example, DOTE supports throughput but assumes a fixed topology, which makes them incompatible with dynamic network condition. Hub and Jaminet handle changing network conditions, but they target other TE objectives. KaeTE is designed for the missing intersection. It realizes both goals in one pipeline. The above limitations point to a natural Stroman solution. The original variables are split ratios R, and they should follow both commodity and link capacities constraints, which are hard to deal with simultaneously. Therefore, KaeTE applies Lagrangian duality to change to the dual problem, which is an unconstrained optimization problem with respect to link variables. Then we can iteratively refine link prices with gradient descent. After the iterative update, split ratios can be recovered from the link prices. However, such Stroman solution still faces some challenges. A finite number of dual updates can still produce lower row split ratios that overload link. and the primal dual mapping is not automatically unique. It leads to the recovery, update, and feasibility challenges met by KaeTE. The first design challenge is a primal recovery, which means how to recover the split ratios when optimal link prices are found. The original throughput objective is linear, so its optimum can be non-unique. To design KaeTE as a demand-weighted quadratic regularizer. The resulting objective is strongly convex, which makes the primal solution unique. Specifically, for fixed link price vector, each commodity can then recover its split ratios with a closed form solutions. The second challenge is convergence within limited iterations. Traditionally, we use hand-designed gradient descent. However, it must choose learning rate schedules. Poor learning rate schedule may result in suboptimal solutions. To this end, KaeTE learns the update procedure via learning to optimize, L2O. It adopts a share per link long short-term memory model to produce update delta from 3 local features: the dual gradient descent, the dual gradient, the link variables, and the link capacities. The same module is shared by every link and across iterations, which is naturally compatible with different link sets and network conditions. The final design challenge is feasibility. While a finite number of dual updates, it can still produce raw split ratios that overload a link. To this end, KaeTE computes every path scaling factor at the maximum utilization among the links on that path, which is also lower bounded by 1. Then KaeTE divides the raw split ratios by this factor to guarantee that no traverse link exists its capacity. KaeTE uses these scaled ratios to compute the the throughput. We then introduce the KaeTE workflow. First, the network operator should specify 2 parameters, namely the iteration time T and the regularization coefficient tau. During deployment, a new traffic matrix, offset, and capacity vector instantiate the constraint primal problem. KaeTE first converts the primal problem to an unconstrained dual problem with respect to link variables, lambda. KaeTE then runs T, a learned refinement step on these link prices with the L2O neural model. At each step, the link prices maps back to split ratios. Finally, a constraint, a well-loss scale those ratios before evaluating throughput. The final output is the objective value and a set of split ratios that can actually be deployed. For evaluation, we first test generalization under dynamic network conditions. We test on a dynamic giant. It contains 50 topologies. We use the first 25 for training, the next 5 for validation, and the last 20 unseen topologies for testing. Here is the result. We can see that we use the normalized throughput, which is defined as the throughput achieved by each learning-based method divided by the optimum achieved by Gurobi. So values closer to 1 are better. At the first percentile, KaeTE can achieve an 89.76%, which is much better than that achieved by TU. This shows the robustness of KaeTE on dynamic network conditions. Next, we show the result on static giant topology. KaeTE also preserves solution quality. Specifically, KaeTE can achieve more than 99% normalized throughput for every testing samples. By contrast, the minimum normalized throughput are 90% for TU and 88% for DOT. To conclude, KaeTE targets a combination that practical neural T has been missing, changing narrow conditions and a capacity-constrained throughput objective. Its contribution is the composition of three ideas: regularization for unique primal recovery, a shared link learn optimizer, and constraint-aware scaling for deployable outputs. The current results show stronger tails on unseen dynamic Gantt topologies and near optimal performance on static Gantt. Thank you.
Any questions?
It's very good application. And I want to ask, I think in most cases, compared to the bandwidth allocation, maybe we concern more about the deadline flows for requirement satisfaction. For example, in some cases, we'll say about, okay, this flow should be completed in 2 nanoseconds, for example, or this flow, the required bandwidth of this flow is for about 10 gigabytes, whatever. So, I mean, in this case, the optimization objective is not maximum bandwidth. So, I don't know, I'm wondering what will the problem look like in this case? If the objective, optimization objective is bandwidth satisfaction or minimal flow latency.
I guess you mean something like for per flow or per commodity satisfaction, right? I think that's another objective, and we will leave it as future work. So this is just a very preliminary result on throughput objective. So in the next step, we can develop more objective like the per maybe something like maximum the concurrent flow. Yeah.
Any other questions? Oh, if no more question, let's welcome our second speaker, Zhang. Zhang is a professor at the University of Electronic Science and Technology of China. His research focuses on networking and communication, and he will present his work. The name is Eagle. So let's welcome him.